Okay, so for the two different genotypes that we have written out, we have the Fisher race one, and that's when you have the 6 different alleles all written out at the same time. So if you had D, C, E, and D, C, E written like that, that's our Fisher race. And then we can turn that into the Wiener form, which is when it's going to be R1 little r, or whatever we're going to turn it into. So remember that Fisher race is one way and that Wiener is the other way. And when you're doing your Punnett squares to figure out the potential genotypes of your offspring, you can do it either way. You can either use the Fisher race or the Wiener notation, and either one is going to give you your results. Sometimes it's easier to do it. It just depends on how you want to do it. This is a nice visual. So when you do it by Fisher race, you can actually see each one of the alleles. When you do it by Wiener, you can only see R1 little r, so you'd have to convert that into its actual alleles that you can see, unless you just have it memorized so well in your head that you know that that's D, C, E, and little d, C, E. So if you have it really quick in your head, then it's not a big deal. Either way, you can do a Punnett square. So remember that you have to inherit one set from your mom and one set from your dad. So this is what I was trying to show you guys in the video earlier. So if we had the mother, who was this, let's just say that same example, they were D, C, E, and they were also D, little c, E. And remember, this is the same thing as if we were saying that they were A, O. Oops. I mean, obviously we're talking about the Rh blood type now, not the ABO, but it would be the same idea of having 2 sets of alleles. We have them in groups of 3 now. Instead of just 1 and 1, we now have 1 with 3 and 1 with 3. So this is the mom. And then dad over here, I never give myself enough space, is going to be, we can pick anything at all. So we can do, we can say D, C, E, and D, C, E, like that. It doesn't matter. These are very rare, but they can still exist. And then this is the dad. I'll just put a F for father, not to confuse you with the D's. And then you can go through and do the same kind of Punnett square that you did before if they were the ABO blood group system. So now we can combine this group of 3 with this group of 3 for the offspring, for a potential genotype for the offspring. So if we start here, we can do D, C, E, slash, because it's one person, we're combining father and mother together for one offspring. So they'd also have to have the mom, which is D, C, E, like that. So this is one potential genotype for an offspring. Then you finish the Punnett square, so you take this same one here with this one this time. So D, C, E from the father, one person, one offspring, so they also have to have the other combination from the mom, D, C, E. So this is a second phenotype option, or genotype, I mean. And then you go down here to the other one. We have little d, little c, big E, slash this one up here, D, C, E. And this one with this one, D, C, E, and D, C, E. So that's how you would predict the potential offspring's genotype. So remember, mom is just like one of the offspring. They have that slash there too. We just broke up their 2 chromosomes. So this would be one chromosome, and this would be the other chromosome, and this is those 3 little locations, depending, or if you think about it under the Wiener notation, it's just one location. And they give one chromosome, or they give the other chromosome, but they don't give both. And the dad's the same. This is one of his chromosomes. This is one of his chromosomes. And together you're going to combine them into one offspring, who has both sets of alleles paired together. This is the offspring's one chromosome, and this is their second chromosome. Here's one chromosome and the other. So they're always paired together, just like before, but it's just a little more complicated because you're combining 6 different alleles all together into one. 3 from one chromosome and 3 from the other. So that's how you pair them together. Just remember that that slash up here is saying that this is one chromosome, this is the other. And then you break them apart in groups of 3 so that you have 3 and 3 from the mom and then 3 and 3 from the dad, and then you can combine all together. So this would be the big way of looking at it. It's like the harder way of seeing it. And then you can predict what the offspring's probability of having that antigen would be. And this is really important when we're talking about hemolytic disease in the newborn. So for example, if the mother had an oh, she's not missing anything. She has every single allele. Oh, no, she doesn't. No, she doesn't have, sorry, she doesn't have, the mom does not have a big E. See, she only has little e here and little e here. She doesn't have a big E. So the mom could potentially develop an anti-big E while she's pregnant. And I gave the dad big E on both of his in this example. So the probability, so that the mom is lacking the big E antigen, she's capable of producing an anti-E in her plasma. And so if she ever did develop an anti-big E, we would actually do this Punnett square out, or we would phenotype the father, and we would predict the probability of their offspring having a big E antigen. And so when we do a Punnett square, but he only has the big E, he doesn't have a little e. And so the big E is going to show up on every single one of these. Every offspring, every 100%, every offspring is going to have an E antigen, which means 100%, if this mom has the anti-E, 100% of the time, the offspring could be affected by it. So this would be one of the examples where we would need to test the father. We would ask for a father's blood. That's an order we can get in transfusion, father's blood. And we would order that, and we would get the father's sample, and we would actually test and phenotype with Antisera. We would use commercially prepared anti-E, and we would actually test his red cells and see if he has an E antigen on it. And then we would test to see if he was homozygous for it or heterozygous. So instead of having to do a genotype workup, we can actually add anti-little e to his red cells and see if the anti-little e was going to react with his red cells. If it doesn't, it shows us that he's lacking the E antigen, which means he only has the big, so he's lacking the little e antigen. He only has the big E, and then we can actually determine what his phenotype is by using Antisera, commercially prepared Antisera. So this is an exact way of determining the probability of the offspring, the baby, the fetus. We can predict the probability of actually having that antigen by doing this kind of Punnett square. And then see what the percent, like the likelihood of the offspring, the fetus, what their likelihood is of actually being affected by the mom's anti-E up here. So I'm going to erase all of this. And I'm just going to show you that you can do it the exact same way with the Wiener notation. So we just did it all with, it's a bit harder to do because you can, well, for me it is, because I always convert it back to Fisher race because you can visually see them. You can look at this. Can you check to make sure it's still lined up? I just moved it. I like to go from Wiener back to Fisher race because I'm more visual. Like R1, little r, I know what it is, but I like to physically see it. So from R1, little r, I know what it is, but I want to visually see each antigen, each allele. So, sorry, this is taking forever. So the other option is that you can do the same type of Punnett square with the Wiener notation. So you can have I'll do a different one. I'm not going to do the same thing, but you can pick R1, you pick R1, little r, and R2, little r, z. And you can do the same Punnett square. Again, you're breaking up, everyone has two. And in this case, we're talking about just one letter in each instead of having three letters. We only have one letter, so it makes it easier to do the Punnett square. So really quickly, this one's an obvious one for you guys. You can do it just like we did the ABO. So this is mom and this is the father. You do your combinations here, R1, R2 from here and here. I always put the capital letters first, R2, little r. I'm doing it out of order, but I always put the capitals and I do it numerically too. So I just kind of combine them in a way that makes it look better for me. And then R1, little rz, and then R, little rz. So looking at that, again, we can predict what the mom might have for an antibody and what the father's phenotype is going to be. And we can predict with the Punnett square what the likelihood of their offspring is to have an antigen that maybe the mom has an antibody to. But like I said, from this version, I don't like to look at it like that. I actually do like to convert it back into the original Fisher race. So I would do this back to D, C, E, and D, little c, E, and D, little c, big E. Again, you can put the slashes if you want, and D, C, E. This little line over the C, remember, represents the lowercase c because they look the same otherwise. So you have to actually put that line over top to show me every time. If you guys don't put that line, I'm going to assume, and anybody else is going to assume it's a capital C. There's a hair there. So just make sure you put that line over top of it to show that it is a little c if you're writing it out. And then down here, we're going to have D, C, E, and the Z. Remember, oh, that's not supposed to be a Z. That's supposed to be a Y. The letters mean that there's all capitals, but the little r means there's a lowercase d. So D, capital C, and capital E, because the Y represents all capitals. And that should be a Y over here as well. And D, C, E, and all capitals, but there's a lowercase r, so lowercase d, capital C, capital E. So now you can actually see all of the different antigens and what is going to be demonstrated on that patient's red cells. And again, if we say that the mom, up here, the mom is, again, she's the same as up here, D, capital C, E, D, C, E. She could have an anti-big E. She could produce an anti-big E because she's lacking that antigen. So it's foreign to her. So if her previous offspring, or if she had a transfusion and she got exposed to a big E antigen, she now could have an anti-big E in her plasma. So when she has a baby with this guy over here, this is the father, we can look at him. R2 is D, little c, E, big E. And now we have little d, big C, big E. He has, once again, the big E on both of his chromosomes, which means he's 100% of the time going to give his big E chromosome. He is lacking the little e. He doesn't have it at all. So the only thing on the E portion he's going to give is big E. So 100% of the time, every single one of these offspring are going to have the big E antigen, which means if mom has an anti-big E, it's 100% of the time going to affect future offspring and could cause future hemolytic disease of the newborn. And again, the way we can test for that now, it's different from the ABO because we didn't have an anti-O other than the H antigen, but like there's still going to be, even if your phenotype was AA, or your genotype, I mean, if your genotype was AA, we can't predict it by antigen testing. We only know that their phenotype is group A. We don't have two separate A's to tell us how many A antigens are on the red cell surface or whatever. So we didn't have a way to actually test for their genotype when it comes to the ABO system. But with the RH system, we can, because we have an Antisera for every single one of the RH antigens. So we have well, we can start with D. We have anti-D, Antisera. We have anti-big C. We have anti-little c. We have anti-big E. And we have anti-little e. So we have every single one of these Antisera. So we can test our patients, all of our patients. We can test their red cells for every single one of these antigens. And we can know their exact phenotype, which then can translate into their actual genotype by testing for these antigens. And then once you know what's present, you can literally have a list of these and say, okay, there's a 4+ reaction. There was a 4+ reaction here. There was a 4+ reaction here. That was negative, and a 4+. Now we're looking, if we actually, this is a good segue. If we did this antigen testing and we set this up, we would have the Rosenfeld way of looking at the antigens. We literally have like the plus, 0, plus. And then we can actually, from here, based on what we have for antigen testing, we can take these reactions and translate them into what their probable phenotype would be, or genotype would be. So we have positive reactions and negative reactions, and we can turn that into, I have to do it out of order, 1, 2, 3. Remember, big E is 3, little c is 4, little e is 5. So then we'd have 1 present, 2 present, 3 is not present, so there'll be a negative beside it. 4 is present and 5 is present. So you're going to take it from that notation, and then you're going to turn it into the Fisher-Race way of figuring out what their likely phenotype would be. Or sorry, I keep saying that, genotype. So this is my segue into the next video. So I will start from here and I'll show you how we go into taking it from this expression here, taking it from this notation, and then actually predicting what their genotype would be. Because we have to put some of them on one chromosome and some of them on the other chromosome. So if we put them together, when we get our results like this, and then we put them together to figure out what chromosome they're going to be on, I'm going to show you how you predict the most likely on the next video.